Imagine a world where math doesn't just explain reality, it increasingly shapes key outcomes. In 2025, three breakthroughs are raising new questions about how far this influence goes. One asks why our most basic sense of chance so often fails. Another reveals how hidden rules of strategy quietly govern markets and even social interactions. And a third confronts the mystery of whether mathematics itself is discovered or invented. Along the way, you'll hear how Microsoft and UC Santa Barbara unveiled progress on topological qubits, part of a wave of breakthroughs transforming quantum computing. But before we reach those frontiers, we need to start with a far simpler puzzle: why our own minds stumble on problems that look like 50-50 choices but aren't. Why our brains fail at probability. Picture this: you're waiting for a bus. Two different routes stop there, one arrives every 10 minutes, the other only every 40. At a glance, your mind frames the situation as an even split between the two showing up next. But the math won't cooperate. Because one schedule creates 4 times as many chances to appear, the odds are nowhere near equal. This simple oversight isn't about transportation, it's about how our intuitions systematically fail when dealing with probability. We gravitate toward symmetry, toward neat 50-50 pictures of uncertainty, even when the underlying numbers tilt heavily to one side. The Monty Hall problem makes this weakness unavoidable. The setup is almost storybook simple. 3 doors, behind one is a prize, behind 2 others nothing of value. You choose a door. The host, who knows everything, removes one of the empty doors, leaving your choice and one other. You now decide whether to stick or switch. To most people, this feels like a 50-50 coin toss between the remaining doors. That's where instinct misleads, because the reality is fixed. If you never switch, you win 1/3 of the time. If you always switch, you win 2/3. Those are the actual odds. This isn't a riddle or a trick, it's conditional probability at work. And what almost everyone skips over is that extra condition, the host's knowledge. We jump to balance instead of following the numbers. So why do our minds default this way? Scientists suggest it's partly evolutionary. Early humans had no need to calculate exact ratios in the wild. If something rustled in the dark, survival favored assuming danger even if the odds were low. Our ancestors built mental shortcuts and rules of thumb, tuned to help them avoid being eaten, not to solve conditional puzzles. These instincts maximize safety but sabotage precision. Psychologists like Tversky and Kahneman showed that the same shortcuts, availability heuristics, confirmation bias, and status quo bias, still steer our decisions today. In Monty Hall, confirmation bias may frame your choice as already right, while the status quo bias makes sticking with it feel safer than changing, even though the math argues otherwise. Research has consistently shown that these biases persist even when people are taught the correct solution. Experiments in recent years asked participants to play variations of the Monty Hall game after walking through explanations of the probabilities. A moment later, under actual pressure, most people kept their first choice. Training does help comprehension, but instinct creeps back in when decisions feel immediate. That gap between knowing the rule and acting on it highlights just how stubborn our evolved shortcuts remain. The struggle appears outside game shows too. Another well-tested bias is the gambler's fallacy. When a random sequence such as coin flips produces several heads in a row, people tend to believe tails is due. They impose balance where there is none, failing to grasp that each new flip is independent. In casinos, that creates illusions of control over roulette wheels or slot machines. In everyday contexts, it leads to reasoning like, I've driven safely for 20 years, so an accident is less likely now, or markets have been down for months, which means they must rise soon. The probabilities, indifferent to human patterns, don't actually adjust to such narratives. These mistakes track back to how we calibrate frequency. People are surprisingly good at relative ranking. They can usually tell that one outcome is more common than another. But extreme probabilities, whether very rare or very frequent, get squashed toward the middle in our minds. In practice, this means we wildly overestimate small probabilities, like the percentage of people belonging to very tiny subgroups, and underestimate large ones. It feels reasonable, but the guesses drift far from reality. A recent example comes from surveys about the proportion of transgender people. The true figure is small, but when asked, respondents averaged much higher estimates. Human judgment drags the extreme toward the comfortable center. Confirmation bias deepens the trap. When we decide on an answer, say, refusing to switch a game show door, we naturally pay more attention to evidence that supports sticking with it. One experiment tracking sports players in competitive situations showed exactly this dynamic. Trailing teams selectively remembered moments of dramatic rallies, feeding the belief we can still win, even when statistics gave little reason for optimism. This filtered recall strengthens confidence, yet undermines accuracy. Optimism is boosted at the cost of reckoning with real odds. Evolutionary psychology offers one compact way to think about it: instincts tuned for survival, not statistics. If you ate a particular berry once and got sick, it made sense to assume danger in the future even if the true chance was tiny. If predators hid in 1 out of 50 shadows, treating them all as dangerous was overcautious but safer than running precise calculations. That bias for overestimating risk and clinging to past decisions protected survival thousands of years ago. Today, in a world defined less by predators and more by data, it leaves us vulnerable to mistakes with probability. Educators have tried to counteract this gap. Long-term studies on probability training show that with practice, accuracy does improve. People get better at identifying independence in coin flips or at recognizing why Monty Hall favors switching, but progress plateaus. Under time pressure or stress, the intuitive brain still drags them back toward symmetry and the fair 50-50. That doesn't mean training is useless. Tools like calculators, diagrams, or structured strategies let people check instinct. Yet stripped of those supports, most revert to the same comfortable misjudgments. Knowledge reshapes the landscape, but instinct never vanishes. Perhaps what is most striking is how universal these limits seem to be. Studies across different countries and levels of education reveal similar results. Whether you're a teenager in Seoul, a retiree in Berlin, or a trained mathematician in New York, the pull toward instinctive symmetry remains. The particular guesses people make vary, but the basic mistake, treating probability as balanced when it isn't, returns again and again. This universality suggests the error is not cultural but biological, a reflection of deep wiring in the human brain. And so probability highlights both the power and the limitation of human thought. Our minds are built to favor stories where choices distill into binaries, yes or no, safe or dangerous, win or lose. But probability doesn't respect narratives. It insists on ratios, on independence, on conditioning. Mathematics makes those rules visible, but intuition resists them stubbornly. Seeing this resistance for what it is changes how you frame everyday decisions. The shortcut that once guarded our ancestors can mislead us badly in a modern world shaped by risk models, health forecasts, and finance systems. The unsettling conclusion is that human beings were never naturally meant to see chance. When probabilities grow counterintuitive, instinct points us astray. The only way to glimpse the real odds is to reach beyond gut feeling with outside structures, mathematics, calculators, and formal reasoning. But that realization raises an uneasy question. If our brains stumble on probability this often, then how can society make reliable decisions in situations where the stakes are far higher than a game show or a bus stop? Probability in the age of AI. In the modern world, probability is no longer only a mental puzzle for humans to wrestle with. It has become the core of how artificial intelligence systems operate. This shift is most visible in what many now call the age of AI, in which machines increasingly make decisions that hinge on probabilistic reasoning. Where human instincts falter, algorithms calculate with steadiness. They take in streams of raw data, test plausible scenarios, and continuously update their estimates without fatigue or bias. The result is a new landscape in which probability has moved from a fragile aspect of human thought to a concrete engine driving real-time choices. Consider the road where self-driving vehicles must constantly manage uncertainty. A human driver glances at a mirror, makes an assumption about speed and distance, and merges based on practiced intuition. The autonomous system approaches this same situation through layered probability models. It evaluates the likely trajectories of nearby vehicles and pedestrians, weighs how weather or road conditions could alter outcomes, and selects the option with the lowest estimated risk. These evaluations draw not only from the car's immediate sensors, but also from collective data gathered across entire fleets of vehicles. Each incident, near miss, or safe maneuver becomes another data point constraining probabilities. The contrast is stark. Where human judgment relies on accumulated personal experience, machines aggregate across millions of samples. This difference makes them more effective at handling conditional probabilities, though it introduces a new problem. While their choices may be more reliable, the underlying reasoning is much harder for people to interpret. In medical systems too, probabilistic models are reshaping what once relied heavily on staff judgment under pressure. Hospital administrators used to plan resource distribution by projecting from past years. Now AI platforms simulate countless patient flow scenarios to determine where doctors, beds, and equipment should be placed. If ambulance arrival rates signal a surge in one region, the system recommends rerouting or rescheduling treatments elsewhere. The probabilities extend to equipment use. Ventilators, blood supplies, or medicine stockpiles are balanced not by rough estimates, but by forecasted odds of demand. In emergencies, this means an ambulance can be diverted mid-route if probabilities shift toward a better survival outcome at another hospital. The logic is different from a dispatcher's instinct. It is probabilistic models running continuous updates, ensuring that rare but high-impact events don't overwhelm the system. Finance offers another arena, though it can be described more briefly. Trading algorithms in 2025 digest global market data, track subtle correlations among instruments, and execute strategies with timing no human could match. What once depended on hunches across noisy trading floors is now reframed as continuous probability assessment across currencies, equities, and derivatives. The emotional highs and lows of investors do not guide the machine, models aiming at fractional advantages do. Similar approaches seep into law enforcement and courts, but here, caution dominates. Predictive tools for recidivism and bail have been trialed and continue to fuel debates about fairness and transparency. These systems may reflect and amplify existing biases, making their application in justice deeply contested. What ties all of these fields together is the same principle. Machines manage probability not as an abstract challenge, but as an operating condition. Where people fall back on rules of thumb, algorithms lean into structured calculations. Yet this very precision generates unease. An AI that judges likelihoods more accurately than a human may still output something that few can explain. For a doctor, patient, or judge, knowing a number is one thing, understanding how that number emerged is another. This interpretability gap shapes the tension between trusting outcomes and grasping methods. People might ask, was the system right? But also, can we see why it was right? Often the second answer is unavailable. These interpretability questions mean that probability in the age of AI is not only about accuracy rates or reduced errors. It is also about legitimacy and acceptance. A probability table written by a human statistician can be unpacked step by step. A probability assessment produced inside a deep network or ensemble model resists such unpacking. Even when the machine is demonstrably more accurate, the opacity of its decisions creates doubt. This tension becomes central in any environment where lives or liberties are at stake. Think back to the driver swerving to avoid an obstacle. A person reacts, guided by habit and instinct. A system simulates likely paths, ranks them, and acts on the minimum risk option. The action looks the same from the outside, a sudden lane change, but the logic beneath it differs. This difference defines the rise of AI. Routine decisions once shaped by gut feeling now emerge from layers of conditional probability processing. The benefit is fewer errors under uncertainty. The cost is a world where explanations become harder to pin down. Hospitals demonstrate the same trade-off. An administrator may justify allocating more staff on a weekend, citing experience of heavy admissions. An AI system, in contrast, recommends shifting staff partly in response to seasonal outbreak data and predicted transit delays. The administrator's explanation feels coherent to colleagues. The AI's depends on correlations across factors too numerous to narrate. Accuracy improves, yet human trust wavers. The system may be right, but people hesitate when they can't connect the reasoning to an understandable story. Even outside headline sectors like health or transport, probability modeling now underpins decisions from supply chains to energy grids. But the pattern holds steady. Machines exceed human probability handling while transparency shrinks. The debate is less about whether machines should operate this way, they already do, than about how humans are to live with opaque but effective tools. The irony is that puzzles once used to illustrate our blind spots, like the Monty Hall problem, have now been scaled up. What was once a classroom example of misguided instincts is now paralleled in systems that define safety on roads, efficiency in hospitals, and patterns of global trade. Our weaknesses gave rise to machine strengths, but those strengths come bundled with new limitations of interpretability and trust. And that leads into the broader pattern. Probability is not the only mathematical lens now shaping institutions. Other frameworks, equally abstract yet firmly practical, govern choices made between people and groups. When individuals or organizations face each other with conflicting incentives, it is not probability that shapes the stable outcome, but strategy. And strategy, too, turns out to follow precise mathematical rules. The hidden logic of Nash equilibrium. Picture two friends standing on the sidewalk debating where to eat. Neither wants to propose a restaurant, worried the other will reject the idea. So they stall, stuck in a stalemate. What looks like a trivial social standoff captures a deeper principle, a Nash equilibrium. In such a state, no one gains by unilaterally changing their choice unless others shift too. The situation is stable, even if it leaves both parties worse off than they'd like. Mathematician John Nash formalized this logic in the mid-20th century. Put simply, a Nash equilibrium describes a setting where each participant's strategy makes sense given the other's strategies, so no one can do better by changing course alone. The crucial detail is stability, not optimality. A group can remain locked in an outcome that is clearly less than ideal, yet because no one improves their situation by moving first, the arrangement continues. Consider the classic prisoner's dilemma. Two suspects are interrogated in separate rooms. If both stay silent, they each serve a light sentence. If one betrays while the other stays quiet, the defector goes free while the silent one suffers. If both betray, both face heavy punishment. The Nash equilibrium in this case is mutual betrayal. Each prisoner reasons that turning in the other avoids the worst-case scenario of being double-crossed, yet both would be better off by cooperating. This illustrates that equilibrium does not mean the best collective outcome. It means the point where strategies stop shifting because individuals fear what happens if they move alone. Economists and strategists have demonstrated the explanatory reach of this framework with larger systems. Nuclear policy during the Cold War, for example, carried the same strategic logic. If one superpower disarmed while the other held nuclear weapons, it risked annihilation. If both retained weapons, neither could act without inviting severe retaliation. Policymakers recognized that deterrence resided in mutual awareness of catastrophic consequences. This balance of armed standoff was not ideal for humanity, but represented an equilibrium state stabilized by fear of unilateral vulnerability. Nash's mathematical lens influenced discussions of deterrence doctrines and transparency agreements, highlighting how stability emerges even in tense political conditions. Environmental negotiations display the same pattern. Each nation benefits in the long run from reducing emissions, but a single government that invests heavily in clean energy risks losing ground to competitors that continue business as usual. No country wants to carry the cost alone. As a result, political leaders often delay, resulting in high global emissions that ultimately harm everyone, even though cooperation would be superior. The game theoretic framing shows why climate progress proves so difficult. Countries hesitate because unilateral action offers no guaranteed gain. Negotiations stall not from ignorance, but from a structural trap created by competing incentives. Corporations exhibit Nash reasoning in competitive markets as well. Imagine two large companies selling similar products. If one cuts prices while the other holds steady, the discounter may gain market share but sees profit margins collapse. If both cut aggressively, both suffer diminished returns. The stable point is for both firms to maintain comparable pricing. From airline ticketing to tech subscriptions, businesses often align in this way, not by collusion but through recognition that bold unilateral moves tend to backfire. The equilibrium locks them in place, frustrating both competition and customers who hope for cheaper deals. Traffic systems reveal another practical angle. Game theoretic reasoning historically influenced rules of the road. When every driver follows the same conventions, say, keeping right at intersections or obeying stoplight sequences, chaos is avoided. If even one driver breaks the rules, risks spike for everyone, including the defector. Economists studying induced demand have extended this framework to explain why building wider highways often fails to reduce congestion. As more people adjust their strategies to use the expanded roads, equilibrium shifts, neutralizing the intended benefit. Road systems thus provide clear everyday evidence of equilibrium logic at work. The principle also appears in cryptocurrency and blockchain networks. These decentralized systems rely on consensus mechanisms. Bitcoin, for example, maintains value because participants agree to follow shared rules. If one validator attempts unilateral rule breaking, the entire system risks collapse, harming even the individual attempting the deviation. Researchers in 2025 observed that the network's resilience stems from this equilibrium condition. Each actor recognizes that deviation undermines both individual and collective value. In practice, equilibrium maintains order in an environment without central oversight. Market behavior mirrors this as well. Traders in cryptocurrency and traditional finance alike balance decisions about holding or selling based on expectations of what others will do. If one fears a sell-off, early selling feels safer. If everyone follows that reasoning, the crash arrives, punishing all. Over time, traders moderate these instincts, creating equilibrium states where sudden mass selling becomes less likely. Algorithmic platforms in 2025 explicitly model trader interaction through Nash-inspired frameworks to monitor stability. By identifying points where no participant benefits from breaking ranks, they aim to prevent cascades that destabilize entire markets. What unites all these examples is subtle. Equilibrium doesn't legislate morality or optimality, it simply maps the incentives. In nuclear arms control, that meant massive arsenals. In climate policy, that meant gridlock. In business, that meant rigid price structures. In traffic design, that meant shared obedience to rules rather than free improvisation. The stability explains why patterns persist even when almost everyone would prefer change. Without coordinated shifts, unilateral moves hurt individuals more than they help. This quality makes Nash equilibrium both powerful and unsettling. It reveals that rational actors may trap themselves in collectively inferior results precisely because moving first carries too much risk. Global problems that look like failures of willpower often rest on mathematical structure. Recognizing this doesn't solve the tension automatically, but it explains why persuasion and goodwill so often fall short when systemic incentives remain misaligned. In teaching or public discussion, the equilibrium sometimes appears deceptively technical, yet its essence is accessible, stability in strategy given what everyone else is doing. This simplicity also makes it striking. When seen clearly, the logic becomes unavoidable: restaurants, roads, markets, climate, security. None of these appear related, yet the same principle describes their behavior. The broad takeaway is not that equilibrium governs every decision humans make. Rather, it explains a wide range of strategic environments where unilateral change offers no advantage. The insight helps reveal why patterns such as standoffs, gridlock, and price rigidity can be remarkably persistent. Change requires collective, not individual action. And that recognition carries into the technologies and platforms that shape daily life now. The same invisible logic that kept nations locked in nuclear standoffs and governments hesitant on climate action also underlies the design of systems that mediate modern social interactions. Stability, even if suboptimal, repeatedly emerges whenever participants cannot improve their position by moving alone. This sets the stage for an uncomfortable realization. The same mathematical structure that forces global powers into strategic restraint now structures much more familiar experiences. In fact, it appears even in the apps and platforms people use every day, silently shaping how interactions unfold. From dating apps to algorithms. Why do some dating apps seem to limit matches, even when millions of people are actively using them? At first, it may look like inefficiency, but the mechanics are more deliberate. Some platforms optimize for engagement rather than immediate results, and scarcity can be one of the tools contributing to longer user retention. The aim is not to connect every user instantly, but to keep the possibility of success always just out of reach. This design choice aligns closely with the kind of stability described in Nash equilibrium. Once the system balances incentives so that leaving appears less rewarding than staying, individuals remain in place even when they sense that progress is slow. This creates a paradox at the heart of digital matching platforms. On the surface, they promise connection, but behind the surface, their structure depends on maintaining active users for as long as possible. If every participant secured an immediate, lasting match, the incentive to return would vanish. Instead, algorithms ensure that results move quickly enough to feel promising while remaining slow enough to sustain engagement. At a practical level, this can mean matches are staggered, limited, or filtered in ways that maintain momentum without ever resolving too fast. For each individual, the cost of leaving early is the sense of missing out on a reward that might appear with one more swipe or a few more days of staying active. Seen through game theory, this is exactly the kind of equilibrium where no single user gains by quitting if most others continue to participate. Consider what happens if one person grows frustrated and logs off. If most others remain, the options outside diminish. The offline pool is much smaller compared to the one still gathered inside the app. Conversely, if everyone left simultaneously, the platform would collapse and no one would benefit. The imbalance of incentives preserves stability. Even complaints about low-quality matches do not break the system because leaving alone feels irrational. Scarcity no longer looks like a flaw here. It fits the logic of equilibrium, where each participant chooses to stay because acting independently offers less payoff. This type of system reveals how platforms shift from seeming like neutral venues to fields of strategy. Every swipe, like, or profile view is input into a structure that sustains itself through repeated incentives. The pattern is less about delivering perfect results than about maintaining equilibrium over time. What matters to the platform is retention, not instant satisfaction. And users, even as they notice the frustrations, reinforce the system through the rational choice to stay if others are staying as well. The same strategic interplay extends beyond dating into broader digital platforms. Social media feeds, for example, are not presented at random. Content is selected by algorithms trained to maximize the probability a viewer will remain engaged. One post leads into another, not accidentally but by design. A user may intend to glance at one update and log off, but the feed arranges itself in a way that encourages one more swipe, one more refresh. This repetition operates like an equilibrium. If you quit scrolling, your own stream of updates shrinks, but since most others keep scrolling, the network still thrives. It is most rational in that environment to continue, even when you recognize your attention is being managed. The important point is that these systems are not simply reflecting user desires, they are shaping them within mathematically stable structures. Platforms compete for time and attention, and those that succeed are the ones that keep individuals from finding advantage in leaving too early. Varying the pace of rewards, curating content frequency, and nudging user response patterns are all ways of fine-tuning stability. As long as the larger population reliably continues, the system does not break down. Resistance requires collective change, which is rare. Individuals instead adapt, reinforcing the very cycle that contains them. Researchers analyzing platform dynamics often compare them to repeated games. Each user trades their time and attention for the possibility of reward, while the system continually updates incentives to keep commitments balanced. This mirrors earlier examples of strategic interaction. Just as nations in standoffs avoid unilateral moves, users avoid leaving platforms so long as others remain active. In both cases, the same mathematical outcome emerges. Equilibrium sustains itself, even when satisfaction is lower than individuals might prefer. Crucially, this state benefits the platform more than the person. In nuclear deterrence, equilibrium preserved stockpiles rather than peace. In markets, it preserved pricing rather than competition. Online, it preserves engagement rather than fulfillment. That misalignment between what helps the system and what helps the individual makes the logic unsettling. A user can feel dissatisfied yet still choose to stay, not from weakness, but because the structure leaves no better solo option. Mathematics predicts exactly this: stable states that resist unilateral change, no matter the discomfort inside them. Understanding this changes how everyday digital habits are interpreted. What looks like an individual shortcoming, spending too long on a feed, swiping despite low results, or chasing a notification, is often the natural outcome of a system designed around equilibrium. Once scarcity and reward are tuned strategically, the repeated engagement of millions is not an accident but the expected result. The same equations used to describe balance in war or economics also explain why scrolling feels endless or why users continue logging back in, even after disappointment. When seen through this lens, the personal struggles many associate with technology begin to look different. Failing to leave a platform is not necessarily a failure of willpower, but a reflection of a structure where rational action aligns with continued participation. Equilibrium creates stability whether individuals are content or not. This is the mathematics working in the background, predictable, persistent, resistant to change one person at a time. And so, when a user finds themselves frustrated with scarce matches or trapped in a continuous feed, it isn't coincidence. It is the signature of stability at work, systems built so that personal exit looks costly while shared engagement looks safer. Once this becomes visible, frustration looks less like personal weakness and more like the outcome of an engineered equilibrium. Seen this way, mathematics becomes not just a way to describe global strategy, but a lens to decode personal technology use. But that recognition leads to a broader question. If abstract models can so effectively explain human interaction inside apps and platforms, what does it mean that the very same language also describes patterns in the natural world? Why should formal symbols and equations predict outcomes far removed from human design at all? The miracle of mathematics in physics. When mathematics moves from classroom abstraction to the heart of physical science, it produces what some describe as a quiet miracle. Its predictions often map onto reality with stunning accuracy. The precision is not limited to one scale. The motion of planets, the collapse of stars, and the strange behaviors of quantum particles all follow frameworks laid out long before direct measurement was possible. This uncanny fit between symbols on a page and physical structures in the universe is what physicists still call the unreasonable effectiveness of mathematics. Its impact is no less profound in 2025 than it was when Eugene Wigner first described the puzzle decades ago. Take quantum mechanics. Before experiments ever had the sensitivity to manipulate or observe single particles, mathematics was already indicating that particles could exist in superpositions, become entangled over distance, and behave probabilistically rather than deterministically. At the time, many of those predictions seemed implausible or even absurd. And yet, once experimental tools caught up, the results consistently matched what the equations had anticipated. Lasers, semiconductors, and MRI machines are direct descendants of formalisms worked out years before any laboratory had the means to confirm them. Here, mathematics did not follow observation. It set the terms that experiments later confirmed. This pattern continues today. The United Nations has designated 2025 the International Year of Quantum Science and Technology, marking the centennial of quantum mechanics. The celebration is not only historical, it reflects the centrality of quantum mathematics to industries now taking shape. Modern investment reports show markets forming around three major pillars: quantum computing, quantum communication, and quantum sensing. According to McKinsey, these sectors together could reach as much as $97 billion by 2035, with quantum computing capturing most of the growth. What started out as abstract derivations has evolved into concrete guidance for where governments and companies place financial bets and how they frame strategies to secure technological futures. Quantum computing illustrates this evolution clearly. Every hardware advance begins with equations. Mathematical models simulate what kinds of particles or circuit designs could resist noise, preserve coherence, and interact reliably as qubits. Developers test thousands of theoretical layouts virtually before building a prototype. Once physical devices are created, their performance nearly always falls close to mathematical projections. By 2025, this has already produced working processors that outperform classical computers on narrow benchmarks, platforms simulating complex molecules with unprecedented precision, and systems exploring encryption strategies resilient to emerging threats. In all cases, the abstract mathematics came first. Experiments later walked the trail it laid out. Not every prediction emerges so quickly or directly. It is important to note that many branches of mathematics are highly abstract, built without reference to nature, and only rarely find their way back into physics, if at all. Entire areas such as category theory, algebraic topology, or pure number theory may wait decades, or may never be linked to experimental science. This nuance is crucial. Mathematics often generates hypotheses beyond immediate experimental reach, and while many have eventually been confirmed, others remain floating without clear physical application. The miracle is not that every mathematical idea mirrors the universe, but that so many of them unexpectedly do. Quantum communication provides a case study. Entanglement was once dismissed as little more than a philosophical curiosity. Yet today, physicists treat it as the backbone of secure communication channels that no classical system could replicate. The market for quantum-secure communication has expanded rapidly in recent years, with prototypes maturing into active deployments. What now appears practical was projected in formal mathematics long before the necessary engineering existed. Quantum sensing reveals the same dynamic, but with even more sensitivity to detail. Equations suggested some systems could measure environmental shifts so fine that no classical instrument could hope to match them. By 2024 and early 2025, two high-profile demonstrations confirmed this. NASA successfully tested an ultra-cold quantum sensor in space, showing that highly fragile states of matter could function beyond Earth's atmosphere. At the same time, quantum magnetometers equipped to navigate where GPS signals fail, such as deep underwater or inside caves, moved closer to real-world utility. These achievements were not trial-and-error engineering feats. They were guided by models predicting that sensors tuned to the quantum level could detect influences invisible to ordinary systems. Similar stories unfold across particle physics. Time and again, equations have described new particles and forces long before accelerators could probe them. Many of the predictions emerged from symmetries and constants embedded in mathematical frameworks, later confirmed by painstaking experiments. Today, laboratories continue that tradition, building machines aimed at reaching the energy scales that theory predicts will yield the next frontier. The reliability of prior forecasts gives confidence that these monumental investments are not blind leaps, but strategic responses to frameworks already pressed into equations. Mathematics sets the coordinates, and physicists build tools to see if the coordinates exist in reality. One striking feature is how branches of math developed centuries earlier for purely logical reasons now serve as the backbone of cutting-edge science. Linear algebra, differential equations, and group theory were not created to explain quantum behavior, yet now they dictate how computations, sensors, and communication systems are modeled. AI-driven navigation devices and microscopes for chip diagnostics operate within frameworks formalized long before anyone imagined their practical use. That continuity between abstraction and application explains why predictions often feel less like guesses and more like the natural unfolding of an already written pattern. Why this happens remains unsettled. Human intuition evolved for survival-scale tasks, tracking animals, reading terrain, avoiding threats. Mathematics, by contrast, captures symmetries and relations beneath those everyday experiences. Whether these relations exist independently, waiting for us to uncover them, or whether we are shaping reality to fit our own invented frameworks is deeply debated. What is not debated is the accuracy with which mathematics underwrites technologies that work. Secure communication systems, diagnostic sensors, or quantum processors. The growing application of mathematics carries economic and strategic weight. Corporations now stake billions on the assumption that math-based models provide trustworthy blueprints for technological development. In fast-moving sectors, planners rely on equations rather than on instinct. For example, the timeline for quantum communication is built less on speculative optimism and more on a consistent record of prior equations, making testable predictions that turn true once technology reaches the necessary precision. Importantly, these successes do not mean mathematics guarantees truth. Equations generate structures of possibility. They highlight relationships consistent with one another, and if those relationships happen to align with physical behavior, breakthroughs follow. At the same time, mathematics produces many constructs with no known physical counterpart. The force of its effectiveness lies not in total coverage, but in repeated success at points where alignment does occur. Each confirmation strengthens the case that mathematics functions not merely as a descriptive tool, but as a bridge between thought and the material world. In quantum technology, this bridging role has become especially visible. Computation, communication, and sensing advance in tandem, each drawing on frameworks written long before engineers could test them. Mathematical models predict outcomes, devices are built, and verification confirms what was already inked in notebooks. The cycle repeats faster than ever, creating a feedback loop between prediction and confirmation that redefines what it means to innovate. That feedback loop reshapes the way we think about science itself. Traditionally, experiments led discovery, and mathematics followed by writing formal accounts of what was observed. Increasingly, the order is reversed. Equations come first, pointing toward outcomes, and experiments act as necessary signposts verifying they were on track. This inversion doesn't make physical science less empirical, but it does highlight how central abstraction has become to directing empirical work. So the phenomenon, often called the miracle of mathematics, may not be mystical after all. Its power lies in a repeatable record of leading researchers into areas that intuition alone would never have suggested. Real-world effects, secure networks, satellite-ready sensors, machines processing information at scales classical devices cannot match or trace their existence to formulations on paper that seemed abstract when first proposed. This historical track record justifies the faith that guides contemporary developments. The takeaway is this: mathematics does not guarantee truth, nor does it predict everything, but it has repeatedly anticipated natural phenomena and technological developments, guiding practical breakthroughs long before direct tests were possible. In this decade, the impact is most visible in quantum technologies, where models scaffold industries expected to become multi-billion-dollar sectors by the mid-2030s. Its effectiveness shows why physics and industry continue to turn to equations not only to describe present reality, but to plot future frontiers. From chalked equations to orbiting satellites, from probability amplitudes to billion-dollar industries, the record of successful alignment between abstraction and the physical world is undeniable. Each new confirmation makes the relationship more puzzling and more powerful. And as 2025 unfolds, the results of this pattern are no longer confined to laboratories or prototypes. They are shaping core systems at the heart of modern science and technology. The consequences of that shift are already being felt, and the next stage will test those equations against one of the most ambitious goals in computing yet attempted: quantum computing and supremacy in 2025. In 2025, the conversation around quantum computing shifted again, with several concrete milestones announced across late 2024 and early 2025. Rather than a single dramatic leap, the progress came as a cluster of benchmark demonstrations that showed quantum processors outperforming classical simulations on carefully defined tasks. Companies released results on entangled logical qubits, on lowering error rates through new correction methods, and on scaling device architectures in ways that make once theoretical applications feel within sight. The phrase quantum supremacy no longer floats as a distant abstraction. Instead, we now see a patchwork of advances suggesting that targeted quantum advantage is here, though universal fault-tolerant machines remain out of reach for several more years. To understand the weight of these announcements, it helps to recall how different quantum systems are from their classical counterparts. A traditional computer builds every calculation out of bits set to 0 or 1, stringing together elaborate sequences of determinate states. Even the largest supercomputers continue to follow those fixed pathways, branching in parallel when they can but never leaving binary certainty. Quantum processors, by contrast, rely on qubits that can exist in superposition, holding mixtures of possibilities. When qubits are entangled, the system collectively encodes information across states that cannot be reduced to simple ones and zeros. It is not that these machines are faster in the ordinary sense, but that they explore entire landscapes of possibilities simultaneously and then collapse to an answer consistent with those probabilities. For certain categories of problems, that shift delivers results unattainable for classical computation. One visible sign of this came through advances in Google's Willow chip, which featured 105 physical qubits with improved error control. Benchmarks in 2024 showed that Willow could execute simulated chemical interactions at scales previously thought too fault-prone, completing targeted calculations that classical supercomputers would struggle to replicate. At the same time, startups and academic labs presented parallel progress. Riverlane demonstrated a hardware-based quantum error decoder designed to process corrections in real time. Alice and Bob reported improvements to cat qubit architectures, designed to suppress errors in their formation. ERA introduced reconfigurable atom arrays, and Atom Computing collaborated with Microsoft to run stabilization schemes for logical qubits. These announcements, taken together, suggest that error correction, long considered the insurmountable barrier, has reached a point where experimental systems can sustain useful operations long enough to matter. The principle behind this is subtle. In classical computing, error handling means copying information and using redundancy. If a bit flips, the system checks against backups. Quantum error correction cannot simply clone qubits because measurement destroys the delicate state. Instead, quantum codes distribute logical information across many entangled physical qubits. This way, small disturbances can be detected by patterns in the collective state and corrected before they cascade. The mathematics that makes this possible comes from algebraic coding theory and statistical inference, where probabilities are calculated for every type of error and patterned redundancies are designed so they cancel each other's effects. Until these schemes could be demonstrated in actual machines, critics argued that the overhead, hundreds or thousands of physical qubits per logical qubit, made the idea impractical. But demonstrations through 2024 and 2025 suggest that the overhead is shrinking and that manageable numbers of physical qubits can already maintain stable logical qubits for limited tasks. Algorithms are the other half of the quantum puzzle. A quantum computer is not designed to replicate classical programs faster. It requires rewriting problems to suit quantum logic. The famous Shor's algorithm showed decades ago that if sufficiently powerful qubits can be stabilized, factoring large composite numbers becomes quick enough to undermine modern cryptography. In 2025, several groups reported new progress on small-scale demonstrations, factoring numbers larger than in previous experiments and building algorithmic variations more resilient against noise. These experiments do not yet threaten real encryption, but they illustrate that the gap is narrowing. Researchers and policymakers treat this not as a distant speculation, but as a horizon problem with real consequences. That horizon is sometimes referred to as Q-Day, the point when quantum computers grow powerful enough to crack widely used public key encryption. The prospect has triggered a swift response across governments and corporations. Authorities in the United States, Europe, and Asia have begun mandating timetables for transitioning to post-quantum cryptography, data protection schemes based on mathematical puzzles outside the reach of known quantum algorithms. Lattice-based techniques, code-based systems, and multivariate polynomial schemes dominate current proposals. Funding streams have accelerated. Billions of dollars are earmarked for migration strategies, and agencies push for international standards to avoid fractured approaches. The consensus is not that cryptography will collapse overnight, but that transition must begin long before practical quantum factoring becomes possible. 2025 therefore marks not a collapse, but the beginning of an organized global migration into post-quantum methods. Financial technologies stand at particular risk. Blockchain systems, for instance, depend on digital signatures and hash functions for integrity. If standard encryption becomes vulnerable, cryptocurrency exchanges, smart contract platforms, and decentralized finance tools all face exposure. In anticipation, developers are experimenting with quantum-resistant schemes. Pilot projects layer lattice-based encryption on top of blockchains, exploring whether the distributed environment can absorb these heavier algorithms without collapsing transaction speeds. Some groups bend hash protocols toward post-quantum variation, while others explore hybrid systems that combine classical resilience with new safeguards. The outcome remains unsettled, but industry interest reflects an unavoidable conclusion. If quantum hardware continues progressing, the theoretical strengths of blockchain demand protection through new layers of mathematics. Security concerns are not the only driver, however. Quantum communication offers a constructive application of the same principles. Rather than defending against quantum attacks solely with harder mathematics, engineers use quantum mechanics itself for protection. Quantum key distribution transmits qubits whose delicate states collapse if intercepted, creating channels where eavesdropping cannot be hidden. By 2024, the global market for such services exceeded $1 billion, and projections for 2035 rose into the range of $10 to $15 billion. In 2025, deployments began to scale. State agencies and financial institutions tested regional networks, and research groups extended the reach of fiber-based and satellite-based systems. Large-scale adoption will take years, but the market mood now treats quantum communication not as a laboratory demonstration, but as an emerging infrastructure. Hardware roadmaps reveal another dimension of progress. The February 2025 announcement from Microsoft and UC Santa Barbara, an 8-qubit topological processor, stood out since topological qubits derive stability from geometric properties of their quantum states. The promise is fewer errors naturally, reducing the heavy overhead of correction. While the demonstration was a proof of concept rather than a functional machine, its symbolism was strong. It indicated real progress toward architectures designed to sidestep some of the weaknesses of current platforms. In parallel, superconducting circuits, trapped ions, neutral atoms, and photonic qubits each showed continued scaling and specialization. No single architecture dominates, and this diversity itself is evidence of momentum. Different approaches aim at the same goal: practical, scalable, fault-tolerant systems. Industry reports reinforce the pace. McKinsey's 2025 Quantum Monitor highlighted projections of up to $97 billion in quantum-related markets by 2035, led by computing but bolstered by communication and sensing. Corporations like Oz, IBM, and Google continue to operate cloud-based quantum services, offering businesses access to prototype processors. Governments increase spending as well, embedding quantum projects into national research strategies and defense planning. Analysts noted that the pace of investment now outstrips the earliest estimates, suggesting an inflection point where quantum technologies transition from speculative venture into scaled development. The narrative is no longer if, but when, and in what form. Yet it is essential to stress the current limits. These systems remain fragile, costly, and specialized. The most advanced breakthroughs still involve narrow tasks crafted to highlight performance edges over classical rivals. Universal machines capable of error-free operation across arbitrary problems are still years away. The steady phrase from researchers is that meaningful fault-tolerant systems remain a multi-year challenge, requiring incremental progress rather than sudden revolution. Still, the signal is clear. Quantum computing in 2025 is no longer hypothetical. It consists of converging threads, improved error correction, new device architectures, algorithms sharpened for advantage, and a growing ecosystem of investment. Each milestone builds toward infrastructure rather than isolated experiments. The buzzword supremacy often hides the nuance, but the nuance itself is important. What we see is not final dominance, but a landscape of significant advantage beginning to emerge. That gradual emergence carries implications beyond the laboratory. Every announcement forces reconsideration of how security, communication, and data management will be handled. Decisions about funding, international standards, and industrial planning now rest on anticipating mathematical and hardware advances rather than waiting until those advances arrive in finished form. Institutions weighing the costs of migration must imagine what quantum processors will be able to do, not only what they already show. It is a new form of strategic thinking, where mathematics again points the way toward the structures of tomorrow. Taken together, the year shows a field moving from experimental curiosity toward systems with genuine consequence. Quantum's role is not yet universal, but it is no longer trivial. Advances in qubits, error correction, and communication frame a trajectory toward technologies that will reshape global computation. The industry's cautious consensus is captured in a reminder. Practical, large-scale fault-tolerant systems remain a target for the future, but the path toward them is visibly narrowing. This moment also prompts a sharper question, one that does not concern only engineers. As quantum devices advance and algorithms reach conditions where humans cannot intuit outcomes, the balance between machine reasoning and human judgment shifts. If processors and AI already demonstrate strengths in probability and strategy, then the challenge becomes deciding what role remains for human intuition. That tension presses increasingly on how we define judgment, responsibility, and meaning in domains not reducible to equations alone. Humans versus machines in decision-making. If machines excel at calculating probability with speed and consistency, the contrast with how humans make decisions becomes unavoidable. In 2025, that difference has come into sharper focus. Where algorithms handle uncertainty with measured precision, people still fall prey to systematic mental errors. What feels like careful reasoning is often a reliance on shortcuts. The persistent question is not whether machines outperform us in statistical accuracy. They do. But whether decision-making requires something more than optimized calculations. Psychologists describe these errors as cognitive biases, programmed tendencies that skew judgment. Recent psychological research catalogs more than 150 of these biases, grouped into themes like information filtering, meaning-making, speed of decision, and memory. Classic experiments by Tversky and Kahneman revealed why human reasoning under risk is so prone to mistakes. Heuristics give fast answers, but often incorrect ones. More recent calibration studies support this, showing our minds tend to compress estimates toward the middle, making rare events seem more common than they are and frequent events seem less certain. For example, repeated statements gradually feel true whether evidenced or not, and vivid anecdotes influence us more powerfully than statistics. These patterns are not random, they are systematic and explain why humans judge probability poorly. Machines operate differently. In tasks like financial forecasting or medical diagnostics, models work by parsing enormous datasets, then distributing weight across indicators without emotional attachment. They do not overweigh the most recently remembered event, nor do they assume a losing streak must soon reverse. When tuned correctly, the system always weighs evidence numerically and proportionally. Without sunk cost fallacy or overconfidence bias leaning on them, machines sustain consistency humans rarely match. For decisions rooted in raw probability, diagnosing illness based on case frequencies or projecting market swings across hundreds of signals, they are more precise and less distorted. Still, replacing human judgment with automated outputs raises limits of a different kind. Prediction and optimization answer one type of question, which option has the lowest risk or the highest likelihood of success, but they leave out another, which outcome best reflects shared values or collective notions of fairness. Legal debates make this clear. Some courts and jurisdictions have tested predictive tools to estimate the chance a defendant might reoffend if released on bail. Mathematically, these scores rank cases with consistency. Yet the tool has faced heavy scrutiny because condensing a person's life into a risk percentage strips away the context communities expect from justice. Use of such systems remains controversial, precisely because prediction by number does not resolve questions of fairness or responsibility. Ethics presents another clear example. Self-driving vehicles must react to sudden hazards, calculating the probability of collisions across possible maneuvers. The machine can specify which choice minimizes risk mathematically, but risks carry moral weight. Who should absorb the harm? Is it acceptable for algorithms to shift danger from passengers to pedestrians or from younger drivers to older ones? Probability curves cannot answer those questions. They are human concerns rooted in cultural, social, and ethical reasoning. In this way, algorithms can supply models of relative safety, while humans must still decide what fairness requires. In 2025, two sectors encapsulate this tension most vividly: medicine and diplomacy. In healthcare, scheduling systems have optimized operating room logistics and staffing. These models can raise efficiency and minimize wasted hours, yet administrators sometimes push back when optimization runs against values like fairness in training or equitable treatment for patients with slim chances of recovery. Machines calculate resource distribution precisely, but human oversight reintroduces balance, insisting that risk reduction cannot be the only criterion. Similarly, in international negotiations, AI platforms simulate trade agreements or ceasefire scenarios, often predicting equilibrium states. But historical grievances, cultural gestures, and symbolic concessions influence how agreements are reached. A settlement that looks suboptimal on paper may persist because it builds trust, a dimension machines cannot quantify. These contexts show how data-driven predictions and human interpretation operate side by side. The distinction matters because it defines where each plays an indispensable role. Machines correct for human misjudgment about uncertainty. People provide the narrative framework within which outcomes hold meaning. Without algorithms, we repeat errors like wrongly expecting balance in randomness or overestimating unlikely events. Without human interpretation, decisions collapse into technical efficiency, stripped of empathy or cultural resonance. Together, they form a dual frame. One calculates, the other contextualizes. The central tension can be stated simply: machines calculate better, humans interpret values better. The contrast explains why institutions rarely hand full authority to either side. In finance, ignoring machine analysis is reckless. Probability models catch errors human traders consistently overlook. In diplomacy, ignoring symbolic context leads to fragile deals that won't endure. Healthcare logistics benefit from machine clarity, but fairness in treatment still requires human oversight. What emerges is a complement rather than rivalry. Each provides what the other lacks. Awareness of this complementarity is crucial. Psychology shows our instincts bias decisions in reliable ways, and we cannot bypass that wiring through willpower alone. But we also cannot outsource decisions entirely to algorithms, because numbers alone do not explain what societies should value. The balance lies in using computational precision to outline options while reserving to human judgment the authority to define which outcomes matter. This split reframes how we think about authority in decision-making. The machine points out probabilities far beyond human intuition. The human weighs which probabilities deserve consequence, whether fairness calls for a higher risk, or whether symbolic gestures mean more than material gains. The fact that both roles are necessary underscores that modern decision-making lives at the intersection of two modes of thought. So what sits at the core of this intersection? Mathematics functions as the language for stripping uncertainty into structure. Human reasoning adds the layers of interpretation that decide what those structures mean. But why mathematics in particular? Why does abstract symbolism carry this strange authority to order outcomes, whether processed by people or machines? The question moves beyond decision-making into philosophy. Does math describe a universal truth waiting to be uncovered, or is it an invented system we insist on applying to the world? That unresolved puzzle sets the stage for the next debate, and it raises one of the oldest questions in intellectual history. Mathematics the real language of reality? Is mathematics something humanity has uncovered, or something we devised? This question drives one of philosophy's longest-standing debates and now feels particularly urgent. On one side lies the observation that mathematics so often describes the physical world with uncanny accuracy, as though its laws were embedded in the universe itself. On the other side lies the argument that mathematics is simply a symbolic language created by people, an invention we use to structure patterns and relationships. Framed this way, the debate has persisted for centuries, yet in 2025 its intensity grows sharper because machines, non-human agents without intuition, are now producing mathematical results themselves. Platonism defines one of the strongest positions that mathematics exists independently. According to this view, numbers, shapes, and structures are timeless entities. Mathematicians discover them rather than invent them, much as explorers discover continents. A prime number exists whether we think about it or not. The ratio of a circle's circumference to its diameter is fixed and eternal, not authored. Platonists point to physics as their strongest evidence. Planetary orbits follow equations. Subatomic particles obey probability rules formalized centuries ago. The consistency of this alignment suggests to them that mathematics is the fundamental architecture of reality. If our number systems were mere invention, it would be a remarkable coincidence that they so neatly anticipate the behavior of galaxies and electrons. Constructivism, however, counters this with equal force. Under this perspective, mathematics is authored, not uncovered. The systems exist only because humans invent them. Symbols, rules, and theorems work like structured games played on paper. 2 + 2 = 4 is accurate only relative to the definitions we established, just as the movements of chess pieces follow conventions we chose. Constructivists acknowledge mathematics has practical impact. It allows us to model planets and atoms effectively. But they argue that this reflects the flexibility of human symbol systems, not evidence of mathematics embedded in cosmic reality. Had human culture chosen differently or not created mathematics at all, planets would still orbit and atoms would still bond. It is our shorthand, not the world's intrinsic design. For centuries, this remained largely a matter of philosophy of mathematics, debated in lecture halls and academic journals. The landscape shifted when artificial intelligence systems began generating mathematics of their own. Programs trained on formal logic and existing proofs have started to propose conjectures and outlines of demonstrations. Their outputs challenge how mathematicians evaluate new results. Are these artifacts mechanical extensions of human-created formalisms, or are they genuine discoveries, accessible to reasoning systems beyond human minds? More cautiously put, machines are now producing content that forces mathematicians to ask whether mathematics must be anthropocentric at all. Already, researchers encounter proofs suggested by AI that stretch human patience and comprehension. Even when these machine outputs require human validation, the very fact they arrive from a non-human source complicates old categories. If the outcomes eventually check out, are we discovering eternal truths, or simply watching a logical engine extend the symbol game? For Platonists, the evidence looks encouraging. If machines can uncover the same structures, it shows that mathematics exists independently of who is doing the reasoning. For constructivists, the argument cuts differently. The fact that systems built purely to manipulate symbols can generate mathematics confirms that the subject is just structured symbol play. Far from resolving the debate, AI sharpens both sides at once. The issue deepens when considering how results are judged. For humans, mathematical elegance, simplicity, and beauty often guide evaluation. Proofs are admired not only for being correct but for forming coherent, intelligible arcs. In contrast, a machine-generated proof may rely on brute force manipulations invisible to human sensibility. When it checks out, it stands, but it lacks the traits humans usually treat as meaningful. This forces a question. If mathematics truly reflects reality, should elegance matter? Or is that just a human bias? If mathematics is purely constructed, then machines churning out proofs without concern for aesthetics may simply reveal that beauty and style were never intrinsic to the system at all. Some contemporary thinkers push further still. Physicist Max Tegmark, for example, has proposed the controversial mathematical universe hypothesis. It suggests that reality is itself mathematics, not merely described by it but literally composed of mathematical structures. Every possible mathematical form corresponds to a possible universe, and ours is one such instance. Although bold, this hypothesis remains highly contentious, embraced by some, but rejected by many scientists who see mathematics as a tool rather than as essence. Importantly, the hypothesis illustrates how debates over mathematics straddle theory, physics, and metaphysics at once. Critics of extreme positions insist on maintaining separation between mathematics as logic and physics as empirical science. They argue that mathematics is a language of assumptions and inference rules. Physics, by comparison, tests the empirical world. Mathematics can describe orbits, predicting eclipses, but abstract conjectures about higher functions may have no connection to nature at all. In this view, some theorems are intellectual exercises, mind games with no external counterpart. That does not diminish their logical rigor, but it underscores that mathematics is not identical with the structure of the cosmos itself. Evaluating AI through this framing gives both schools a new foothold. Constructivists interpret machine-generated mathematics as confirmation that the subject depends on symbol manipulation. If an algorithm can generate results, it exposes the non-mystical, human-authored nature of mathematics. Platonists interpret the same evidence differently. If an artificial system can uncover truths we had not spotted, then those truths must exist outside human culture altogether, waiting for discovery by any competent agent. This dual interpretation shows how 2025 has taken the debate from abstraction into practice. Both interpretations find validation, yet neither closes the discussion. The debate is not purely theoretical. It seeps into questions of authorship, intellectual credit, and trust. If AI outputs a correct but opaque result, should it count as a discovery? Should mathematicians list AI as co-author? At what point does a mechanical contribution rise to the level of human creativity or scientific insight? Already journals wrestle with whether machine-assisted proofs fulfill publication standards. Arguments about invention versus discovery now shape policy about how results are trusted, credited, and circulated. The uncertainty also influences how mathematics is taught and understood. If automated systems can generate intricate structures faster than humans can analyze them, then should emphasis shift to interpreting and contextualizing results rather than creating them by hand? For educators, the prospect raises questions about whether mathematical creativity is uniquely human, or whether interpretation becomes our main role once generative systems take over baseline construction. What emerges then is not resolution but sharpening tension. AI acts as a mirror, reflecting our assumptions about mathematics back at us. Some see AI results as evidence of mathematics' independence, others see them as confirmation of its artificiality. The same proofs sustain entirely opposite philosophies. What is new is that events demand practical responses, decisions about trust, publication, and validation that cannot wait for an ultimate metaphysical answer. The broad takeaway of 2025 is that mathematics remains both indispensable and unsettled. Its authority is unquestioned. We use it to structure physics, finance, cryptography, and computation. But its nature, what mathematics truly is, remains elusive. Machines have not solved the debate, they have forced it into daily practice. The 2025 reality, then, is this. AI has shifted the discussion of mathematics from a distant philosophical puzzle into pressing questions about authorship, verification, and trust. Whether mathematics is invention or discovery remains open. What is certain is that modern life runs on its outputs, even if the essence behind them resists final definition. And as these questions circulate, they connect back to a more immediate concern: what mathematics means for people navigating probability, strategy, and reality today. The deeper questions remain unsettled, but their effects shape practical decisions we already live with. What this means for us in 2025. What does all of this mean for us living in 2025? The lessons of probability, game theory, and the mathematical structure of physics are not abstract debates. They shape the systems and choices that surround us every day. The details of funding, investment, and security planning may feel distant, but their consequences are close. To see where we now stand, it helps to distill the lessons into three simple but profound points. Mathematics corrects our instincts and powers the systems around us. Nash-style incentives stabilize institutions and platforms, even when outcomes are imperfect. And quantum science has pushed mathematics into the core of strategic investment and technological infrastructure. Each point is visible not in theory but in practice. First, mathematics corrects the limits of human intuition and powers real-world systems. We know our own minds predict chance poorly. Probability often betrays our instincts about fairness and balance. Machines step into this gap, applying the mathematics of prediction and optimization to everyday processes. In hospitals, predictive systems allocate staff and resources before shortages appear, a task only possible through large-scale probability modeling. In global finance, algorithms monitor risk across multiple markets and adjust flows in ways human traders could never match. And in transport, navigation systems constantly update routes, comparing millions of probability-weighted paths to avoid congestion or maximize fuel efficiency. None of these actions feel overtly mathematical to the individuals using them, yet every one rests on calculations that improve outcomes far beyond what intuition could supply. The quiet presence of probability in daily systems demonstrates how mathematics silently stabilizes everyday life. Second, Nash-style incentives stabilize social, economic, and political systems, even when results leave us unsatisfied. Equilibrium logic explains why nations maintain standoffs, why companies align prices, and even why users remain locked into digital platforms that frustrate them. Stability emerges not because anyone consciously plans it, but because unilateral changes tend to punish individuals more than they help. On dating apps, for example, scarcity of matches prolongs engagement, not because users desire inefficiency, but because leaving alone feels costlier than staying while everyone else remains. In environmental policy, governments delay emissions reductions for fear of losing competitive advantage, even while cooperation would benefit all. The structures persist not through intent but through mathematical stability. And those locked into the system are often aware of its flaws, yet find themselves perpetuating it because deviation alone offers no improvement. Equilibrium thus explains why even unsatisfactory situations endure and why change often demands collective action, not individual courage. Third, quantum mathematics now drives investment strategies and infrastructure planning with urgency. After decades as primarily a scientific pursuit, quantum technology has become an industrial race. Stabilizing qubits, once a fragile laboratory goal, is now an engineering challenge drawing billions of dollars in funding. McKinsey projects the industry could reach $97 billion by 2035, with quantum computing alone rising from $4 billion in 2024 to as much as $72 billion. This scale of growth explains why nearly $2 billion was invested in quantum startups in 2024 alone, a 50% increase from the previous year. The momentum is visible in specific breakthroughs, such as Microsoft and UC Santa Barbara's recent 8-qubit topological processor, a step toward qubits less prone to noise and error. These developments underline why nations treat mathematics as more than an intellectual pursuit. They treat it as strategic infrastructure in the same way as energy grids or transport networks. To control these systems is to secure a foothold in the technologies upon which economies, communication, and security may depend. This condensed view makes the implications clearer. Mathematics is no longer just a support tool for science or finance. It has evolved into a central, invisible infrastructure for many of the systems on which we rely. We may not notice the equations at work, yet they shape the choices available to us. Which routes appear on a map, which posts rise in social media feeds, which medications reach pharmacies, and which investments flow into markets. As with physical infrastructure, we only truly notice mathematics when it falters, when a supply chain breaks, when a risk model fails, when a system built on poor incentives collapses under stress. But in its ordinary state, mathematics is the silent support beneath our daily decisions. The surge in quantum technology offers perhaps the most striking illustration of this transformation. Communication firms now prepare for Q-Day, when current cryptography may fail under sufficiently powerful quantum computers. Markets are already responding, with spending on post-quantum cryptography forming one of the first commercially mature verticals in the broader quantum sector. Likewise, quantum sensors have begun moving from laboratory demonstrations into real fieldwork, with applications as varied as military navigation in GPS-denied zones and diamond-based microscopy capable of pinpointing semiconductor failures. These are not distant promises but real-world deployments, funded heavily because the mathematics behind them has already proven reliable. Progress like NASA's ultra-cold sensor test in space or Microsoft's logical qubit stabilization experiments underscores how equations precede prototypes, and prototypes create industries. Investments follow not out of speculation, but out of recognition that mathematics predicts usable outcomes. Public and private sectors now treat these equations as levers of power. The Australian government pledged over $600 million toward building a fault-tolerant quantum computer. Illinois announced $500 million for a new quantum park. Japan committed $7.4 billion to the sector in early 2025. Even smaller nations, from Singapore to Spain, are allocating hundreds of millions. These are not acts of curiosity. They are strategic bets on infrastructures still emerging. The sums confirm that nations now rank mathematics among defense priorities. In their eyes, whoever enables the most stable, scalable qubits controls technologies that can bend finance, communication, defense, and science around their capabilities. In that sense, mathematics in 2025 occupies a position nobody could have predicted a century ago. It does not only structure theories about the cosmos or refine engineering models. It defines the flows of capital, the directions of national investment, and the defenses of critical information. And because these equations consistently anticipate capacities that experiments later confirm, government planners and corporate strategists cannot afford to ignore them. To do so would be to fall behind, as the material world continues to align with mathematical frameworks already tested on paper. That reality has direct consequences for individuals too. Sending a secure message, swiping through a platform, applying for a loan, or relying on a navigation system may feel like purely human tasks. Yet behind them stand systems that align incentives, calculate probabilities, and project quantum-secured futures. Mathematics determines which options are offered and which disappear before a person even notices. We do not always see its hand, but it is present from the personal level to the geopolitical scale. Taken together, these developments show why mathematics in 2025 should be regarded less as background knowledge and more as a functional operating system. Like an electrical grid, we take it for granted while depending on it absolutely. Its relevance is visible not just in philosophical questions about whether math is discovered or invented, but in the material infrastructure of markets, security systems, transport routes, and research budgets. The numbers are no longer silent abstractions on chalkboards. They are active, directing the directions of economies, securing the privacy of communication, and shaping the strategic calculations of entire nations. If there is a lesson to draw, it is that ignoring mathematics is no longer an option. For centuries, people lived well without knowing calculus or quantum theory, relying on only basic arithmetic in daily life. But in 2025, the structures of society increasingly rest on equations that define the flow of capital, the resilience of security systems, and the stability of interactions. To disregard them is to disregard the rules that quietly but decisively guide civilization. Mathematics explains why our instincts fail, why equilibrium holds us in standoffs, and why whole industries rise or fall on predicted capacities. It explains, as well, why nations commit billions to infrastructure made not of steel but of equations. We now face a choice about how to engage with this reality. Some will resist, treating mathematics as background noise, a tool left to specialists. Others will adapt, learning to interpret the probabilities and incentives that shape their environments, recognizing that even if mathematics cannot dictate what we value, it does outline what is possible. The practical world increasingly rewards those who acknowledge the mathematical scaffolding beneath modern life. The question is not whether mathematics matters in 2025, it clearly does. The question is how we, as individuals and societies, respond to its authority. Will we resist until forced to adjust, or will we adapt while there is room to do so deliberately? That tension defines the years ahead, and it sets the stage for the reflections that follow. Mathematics now shapes the world around us in ways that feel unavoidable. From algorithms curating what we see online to quantum processors guiding billion-dollar investments, numbers have become part of the infrastructure of daily life. In 2025, they are no longer just abstract ideas, but active forces influencing choices at every scale. Numbers do not dictate outcomes absolutely, but they strongly influence them. Understanding that influence helps us make better decisions rather than leaving them to chance. So is math the language of reality, or simply our best tool to describe it? The question remains, tell us what you think. If this surprised you, comment with one area where you'd like to see math explained, crypto, AI, or daily decisions, and subscribe for clearer breakdowns.